What if I told you that splitting up a piece of software to make it run faster could actually, accidentally multiply its baseline carbon footprint by 10?
Yeah, that is a pretty wild statistic to start with.
Right. Well, welcome to today's deep dive. We were looking at a really fascinating stack of sources today. It's three academic study guides from an IT module.
Right. The Digital Intelligence for Sustainability module.
Exactly. And it covers like cloud architecture, application patterns, and performance trade-offs. Plus, there's a related technical quiz in there, too.
Hmm.
So the mission for this conversation really is to uncover the hidden energy and performance costs of how software is actually built and deployed.
Yeah, because we're looking for that shortcut, right? To understanding that making IT sustainable for you isn't just about, buying carbon offsets or plugging a server into a wind turbine.
Right.
It is about the fundamental architecture, because the architecture sets this hard floor below which no amount of clever code-level optimization can ever reach.
Okay, let's unpack this because before we look at the physical locations where our software runs, the sources suggest we have to examine how we split the software up in the first place.
Right, the actual structure of the code.
Yeah, and the industry standard right now is just this absolute obsession with microservices. Like
Yeah.
every modern engineering blog treats them as the ultimate default architecture.
They really do. But the assumption that microservices are inherently more modern and, therefore more efficient is, it's one of the most pervasive myths we really need to question.
Okay, so why is it a myth?
Well, we have to look at the physical energy cost of how these systems communicate. So think about a traditional monolithic architecture where the entire application is just bundled together.
Like one giant chunk of code.
Exactly. When one part of the code needs to talk to another, say, the checkout system verifying inventory, that internal call, is just an in-process memory jump.
Right.
The processor merely points to a different address in the RAM. It takes fractions of a microsecond. There's zero network traffic, zero translation.
It makes me think of the analogy from the sources, right? Like a monolith is basically a family living in one house. Passing the salt happens instantly. You just hand it over.
Yes, that's a great way to look at it.
But when you fracture that monolith into microservices, you are essentially putting everyone in separate houses. And now they have to like physically mail the salt back and forth. You're taking that instantaneous memory jump and turning it into this massive logistical operation.
What's fascinating here is the sheer amount of computational work required just to pass a message in that scenario.
Right, because it's not just pointing to memory anymore.
No, not at all. The calling service has to extract the data, serialize it, meaning it translates that raw memory into a transportable format, usually like JSON or protobuf, and then it hands it down to the network stack.
Which is a whole other process.
Exactly. The network stack packages it into packets, pushes it through a virtual or physical network interface, sends it across the wire, and then the receiving service has to do all that in reverse. Yeah, it catches the packets, unpacks them, parses the JSON back into memory, and only then can it actually execute the inventory check.
That sounds exhausting for a computer. And the sources actually give a really stark mathematical comparison for that overhead. Like, a user request to a monolith might trigger an internal call chain that completes in about 2 milliseconds.
Right. Super fast.
But if you take that exact same logical request and fan it out across, say, 8 independent cooperating microservices, you are suddenly executing 8 network round trips.
Yeah, and each of those trips adds 2 to 5 milliseconds of pure network and serialization overhead.
It means your total response time becomes like 15 to 30 times longer.
Exactly. Which also means it consumes proportionally more energy across all those participating services. And, we haven't even touched on the baseline infrastructure costs yet.
Oh, right, the environments.
Yeah, every single microservice you spin up requires its own supporting environment.
Yeah.
It needs its own language runtime, its own memory allocation, and crucially, its own health probes.
I really want to zoom in on that, actually, because a health probe sounds like a tiny, harmless little feature.
Right, it sounds helpful.
Yeah, but it's essentially a constant digital heartbeat. The infrastructure is just constantly polling the service, asking, are you alive? Are you alive? Are you ready for traffic? Every few seconds.
24 hours a day, 7 days a week.
Just nonstop.
Precisely. That heartbeat requires the CPU to wake up, process the network request, and send a response. And sure, it consumes microscopic amounts of electricity each time.
But it adds up?
Oh, absolutely. When you multiply that by dozens or hundreds of microservices running continuously regardless of actual user traffic, you are burning a massive amount of baseline power.
So splitting up the code just multiplies the waste.
Yeah, if you take a moderately sized monolith and split it into 10 microservices, you frequently multiply your baseline energy footprint by 10,
Yeah.
and you do that without gaining any functional advantage.
But the defense I always hear for that architecture, though, is dynamic scaling, right? Like the idea is that if I have a massive spike in user logins, I only have to scale up the authentication service.
Right, that's the classic pick.
I don't have to duplicate the entire monolithic application, which theoretically saves power.
And that logic holds up, sure, if you are operating at a massive global scale.
Like Netflix or Amazon.
Exactly. If you are a giant tech conglomerate where individual features experience wildly divergent traffic spikes, yeah, microservices prevent you from provisioning unnecessary global infrastructure. But for the vast majority of companies,
It's overkill.
completely. That level of granular scaling is entirely unnecessary. The baseline tax of running the distributed system completely eclipses the occasional savings from targeted scaling.
Which is why the study guides actually advocate for the modular monolith as the smartest compromise for most teams.
Oh, the modular monolith is fantastic.
Yeah, you still enforce strict boundaries in your code, so the authentication team doesn't tangle their code with the inventory team, but it all compiles and deploys as a single application.
You get the organizational cleanliness of microservices, but the communication remains that instantaneous in-process memory read.
You completely eliminate the network tax.
Exactly. It is a highly sustainable middle ground. It acknowledges the reality of how engineering teams actually operate without, sacrificing the physical efficiency of the hardware.
But, okay, if the core problem with microservices is the baseline energy wasted on idle infrastructure and those continuous health probes, then my gut says serverless computing should be the ultimate solution.
Oh, I see where you're going with this.
Right, because a serverless function literally scales to zero. It doesn't exist until a user clicks a button, and then it just vanishes when the job is done.
Yeah.
Isn't that the ultimate green hack for our listeners' next project?
You would think so, but that assumption leads directly to what the sources call the serverless paradox.
The serverless paradox. Okay, tell me about that.
Well, serverless architecture is brilliant for very specific workloads, but it can actually drastically increase your energy footprint because of the mechanics behind the cold start.
I'm trying to visualize this. If the code doesn't exist on a running server, how does it suddenly execute when a user makes a request?
That's the catch. It doesn't happen instantly. When a request hits a serverless endpoint that has scaled to zero, the cloud provider's control plane has to scramble.
Like it has to build the environment on the fly.
Exactly. It must provision a brand new virtual environment or container, load the underlying operating system and the language runtime, then download your specific function code from storage and boot the application framework.
That sounds like a lot of steps.
It is.
Yeah.
That initialization process, the cold start, can take hundreds of milliseconds or even several seconds, depending on the programming language you're using.
So you are expending this massive amount of CPU cycles just setting the stage before you even begin processing the user's actual request.
Exactly. Imagine you need to charge a highly efficient electric toothbrush, right? Which takes very little power.
Okay.
But the only way to do it is to cold crank a massive industrial diesel generator, wait for it to idle smoothly, plug in the toothbrush for 20 minutes, and then shut the generator entirely down again.
Oh, wow. That is incredibly wasteful.
Right. The energy spent starting the heavy machinery vastly outweighs the useful work done. The sources highlight this specific ratio. If your function only requires 20 milliseconds of actual computation, but you pay a 500 millisecond cold start penalty just to wake the environment up.
The vast majority of your energy expenditure is pure overhead.
Exactly.
That paints a really clear picture of why serverless is perfect for unpredictable, bursty traffic. Like if a script only runs 3 times a day, keeping a server idling 24/7 for that is a colossal waste of power.
Right, serverless completely eliminates that idle waste.
But for a steady, high-volume stream of traffic, say, hundreds of requests per second, serverless becomes a liability.
A huge liability. You are constantly hitting cold starts as the platform recycles containers to manage the load, so you're paying that initialization tax over and over and over again.
So at a high continuous volume, a dedicated, long-running server that is already warm and waiting in memory is fundamentally more energy efficient.
Yes, exactly.
Okay, so if computational time is that precious
Yeah.
and waking up environments is that expensive, it seems absolutely critical that we don't waste that processing power handling data the user doesn't even want.
Right.
Which naturally brings us to how these architectures move data around, specifically the APIs.
Yeah, network energy is directly proportional to the volume of data transmitted. And traditional REST APIs have this structural flaw here, commonly known as overfetching.
Overfetching, right.
A REST endpoint is designed to return a fixed, predefined structure of data, regardless of what the client actually needs.
The example in the study guide for this is just wild. So an application just wants to display a user's name and email address on a mobile screen.
Simple enough.
Right. It queries the standard REST endpoint, but the server is programmed to return the entire user object. So it sends back the name, the email, but also the account creation date, the physical mailing address, their marketing opt-in preferences, and like a high-resolution avatar URL.
Which is huge.
Yeah, the application pulls down a 4.2 kilobyte payload across a cellular network, extracts the 0.4 kilobytes it actually cares about, and just throws the rest away.
The physical cost of that wasted data is staggering when you multiply it by millions of users. I mean, it is not just the transmission energy consumed by the cell tower and the phone's radio antenna.
But the server had to work for it too.
Exactly. The server had to spend CPU cycles retrieving those extra 30 fields from a database and serializing them into JSON. And then the mobile device had to spend battery power parsing that bloated JSON payload just to find the 2 fields it needed.
And the solution they point to for this is GraphQL, right?
Yes, GraphQL is brilliant for this.
Because instead of a fixed menu where you are forced to order a massive banquet just to get a side of fries, GraphQL acts like a precise query language.
Right. The mobile app explicitly asks the server for the name and email, and the server processes and returns exactly those 2 fields. Nothing more.
So the energy savings on network transmission alone are immense, particularly for, mobile edge devices operating on 5G networks where radio transmission is super power intensive.
If we connect this to the bigger picture, we are really dealing with some intense structural constraints here.
Yeah.
We know we can't rely on serverless to instantly absorb massive traffic without paying a huge cold start energy penalty. But we also know that keeping giant traditional servers idling at maximum capacity 24/7 just in case a traffic spike happens is incredibly wasteful.
So how do we handle unpredictable surges in demand then?
Well, that tension is exactly why enterprise systems rely on event-driven architecture and asynchronous processing. We basically have to decouple the arrival of a request from the execution of the work.
Okay, think of a massive logistics port.
Yeah.
If a port operated synchronously, they would have to hire like 10,000 dock workers to just stand around doing nothing, just in case 50 cargo ships arrived at the exact same hour.
Right, which is ridiculous.
Yeah, they'd have to size their workforce for the absolute peak maximum load, which is financially and practically impossible. Instead, ports operate asynchronously. They have a massive holding yard, a buffer.
Okay, I see where you're going.
When 50 ships arrive, the containers are unloaded into the yard. Then, a steady, predictable crew of workers processes those containers from the yard onto trucks at a highly efficient, continuous pace.
And in software, that holding yard is the message queue.
Exactly.
In a synchronous architecture, if an application averages, say, 10 requests a second, but it spikes to 200 during a promotion, the engineering team is forced to permanently provision infrastructure capable of handling 200 requests a second.
Because if they don't, the 201st request hits a saturated server, and the entire system crashes.
Right. Which means 95% of the time, that massive infrastructure is just sitting idle, drawing power, waiting for a spike that isn't happening.
But in an event-driven system, when the user clicks a button, the system essentially just hands them a digital receipt. It drops the task into the message queue and says, we'll get to it.
Exactly. The consumers, meaning the back-end servers, doing the heavy computational lifting, they pull tasks from that queue at a steady, optimized rate.
They never get overwhelmed.
Never, because the queue acts as a shock absorber. You don't need to over-provision the compute layer. You just let the queue grow temporarily during the burst, and the workers catch up when the traffic subsides.
There's a fantastic case study in the sources about this. It's about an e-commerce platform that processed product image uploads.
Oh, the thumbnail generation one.
Yeah. Sellers would bulk upload thousands of catalog images, which required the system to immediately generate small thumbnails, but it also had to perform a very heavy 30-second AI scan to check for prohibited content.
Right. And they engineered a brilliant hybrid solution for that. They routed the lightweight, predictable thumbnail generation directly to serverless functions.
Because it's fast.
Exactly. That allowed the system to instantly scale up and absorb the massive, unpredictable burst of uploads without maintaining idle infrastructure. But they kept the heavy 30-second AI analysis on a dedicated pool of long-running worker servers pulling from a message queue.
Because if they ran a 30-second task on serverless,
Oh, they would hit timeout limits and pay astronomical execution costs. The queue protected the AI servers from the traffic spike, ensuring they ran at maximum efficiency 204/7 until the backlog was cleared.
it perfectly illustrates how matching the architectural pattern to the specific, temporal nature of the workload optimizes both the cost and the energy.
It really does.
Okay, here's where it gets really interesting. We figured out how to shape the code and how to manage the flow of time. But where on the physical planet should this code actually live?
The physical deployment?
Yeah, because my instinct is that if I want to be a truly sustainable engineer, I should just deploy my entire infrastructure to a data center powered by a geothermal plant in Iceland.
Right, the Iceland approach.
Yeah.
Well, carbon intensity is only one of 5 factors in region selection, and in the real world, these factors constantly exert friction against one another.
What are the 5?
The 5 are latency, data residency, redundancy, cost, and carbon. If you deploy your application to Iceland, but your customer base is in Sydney, Australia, you immediately run into the unyielding physics of latency.
Oh, because of the distance.
Yeah,
Actually, the study guide notes that light takes about 70 to 90 milliseconds just across the Atlantic Ocean through a fiber optic cable.
right. And interactive applications start feeling noticeably sluggish to users once the round-trip delay exceeds 150 milliseconds.
So your beautifully green Icelandic server might render your application functionally unusable for your actual customers in Australia.
Exactly. And then you encounter data residency, which is entirely geopolitical.
Right. The sources detail a case study involving a Gulf regional bank, right?
Yes. They were executing this major modernization project and evaluated migrating their backend to a European cloud region because it offered a highly renewable energy grid and very competitive compute costs.
But they had to abandon that plan entirely.
Completely. National banking regulations legally mandated that all citizen financial data had to physically remain on servers located within the country's borders.
So the legal compliance just completely vetoed the sustainability and cost metrics.
Did, which forces us to look at redundancy and deployment patterns. To guarantee uptime, modern systems replicate themselves across multiple geographic regions. And the two dominant paradigms here are active-active and active-passive.
I always viewed having a backup server as just standard operational hygiene. Like you just have to have it.
Fair for resilience.
But the quiz section of the material makes it painfully clear that the active-passive pattern is a severe sustainability flaw.
It really is. Consider the physical reality of an active-passive setup. Your primary region in New York is handling 100% of the user traffic.
Okay.
Your passive, secondary region in Texas is handling 0 users. However, to be ready to failover instantly, that Texas region must continually power vast database arrays, constantly writing data to keep perfectly synchronized with New York.
So it's basically doing all the heavy lifting but helping nobody.
Right. It is maintaining active network tunnels, running health checks, and holding memory states. It is a massive industrial engine idling indefinitely, consuming immense power without producing a single cycle of useful work.
Wow. Compare that to active-active, where both New York and Texas are actively serving portions of the user base. You are fully utilizing the hardware you provisioned in both locations.
There is 0 idle waste in that scenario.
And to handle the latency issues of users being far from those primary data centers, the sources emphasize CDN's content delivery networks.
Yes, CDNs are crucial.
By catching static files and images in smaller edge data centers physically closer to the users, you prevent those requests from ever having to cross the ocean to the origin server. It dramatically cuts the transmission energy.
This raises an important question, though. When engineering teams are confronted with this, web of intersecting constraints, latency versus carbon, caching complexity versus database load, legal compliance versus cost, how do they actually make architectural decisions without just guessing?
Yeah, I look at all these trade-offs, and it feels inevitable that if I want to build a highly resilient, ultra-fast application, I am going to have to burn more power. Like, performance and sustainability feel like opposing forces.
That is one of the most common illusions in software engineering. The sources deliberately distinguish between real tensions and illusory tensions.
Okay, what's the difference?
Well, in the vast majority of scenarios, performance and sustainability are actually aligned. They're pulling in the exact same direction.
Because at a microscopic level, a faster application is just doing less work.
Exactly. An algorithm that executes in half the time is literally executing fewer CPU instructions. That means the silicon logic gates are switching fewer times, which directly translates to less electrical power drawn from the motherboard.
That makes total sense. And a smaller, more compact data payload transmits faster over the network, which means the radio antennas on a mobile device can power down sooner, saving battery and network energy.
Right. Right-sizing your server infrastructure prevents requests from queuing up in overloaded memory buffers, making the application more responsive while simultaneously drawing less power than an oversized, underutilized server array.
So the idea that green software is inherently slower or less capable is fundamentally false.
Totally false.
But what about the real tensions? Like, where do teams actually have to make painful sacrifices?
Real tensions occur in very specific edge cases. For example, extreme cache freshness.
What does that mean?
Well, if your business model requires users to see the absolute real-time updated number on a dashboard, you have to constantly invalidate your edge caches and force the central database to compute the answer from scratch every time.
Ah, so you are sacrificing the massive energy efficiency of a CDN just to gain a few seconds of data freshness.
Exactly. Another real tension is provisioning idle capacity to absorb unpredictable, massive traffic spikes when you can't use a message queue for whatever reason.
And when teams hit those genuine roadblocks, the framework that sources recommend is multi-criteria decision analysis, or MCDA.
Yes, MCDA is so helpful here.
Instead of a senior engineer just picking their favorite tech stack and rationalizing it later, MCDA forces the team to explicitly list their criteria, latency, cost, carbon footprint, compliance.
Right, get it all on the table.
Yeah, and then they assign a numerical weight to each based on the business goals and score the architectural options against that matrix before a single line of code is ever written.
It introduces rigorous objectivity, which perfectly mirrors the green software maturity progression outlined in the study guides.
The 4 stages, right?
Yes. Organizations do not simply declare themselves sustainable overnight. It is an evolution: awareness, measurement, optimization, and finally, integration.
And the sauce company case study highlights how uneven that progression can be within a single organization.
Oh, yeah. That's a classic example.
They conducted an internal audit and discovered their core platform infrastructure team was already operating at stage 3 optimization.
They had dashboards tracking compute emissions. They were actively right-sizing their clusters. They were doing great.
But their product engineering teams, the people actually writing the user-facing features, were stuck at stage 1 awareness. They had 0 metrics and didn't even know how their code impacted the cloud bill.
The critical takeaway there is that leadership cannot mandate the entire company to instantly jump to stage 4 integration. It must be staged.
You have to walk before you can run.
Exactly. You have to implement the telemetry to get the product teams measuring their impact first, before you can expect them to optimize it. Ultimately, sustainability has to become embedded directly into standard code reviews and architectural planning.
Treated with the exact same severity as a security vulnerability or a performance bottleneck.
Precisely.
So, what does this all mean? We began this deep dive talking about how a physical building has an obvious, visible footprint. What we have uncovered is that the digital architecture of our software sets the absolute energy floor of any product we interact with.
Yeah.
Whether you are an engineer writing the code, a product manager prioritizing the roadmap, or just a user pulling out your phone, you now know that every single digital interaction has a physical thermodynamic cost.
It does.
And that cost is dictated by invisible design choices. Synchronous queues versus asynchronous buffers, monolithic memory jumps versus microservice network taxes, active utilization versus active-passive waste.
It is a profound realization that forces us to look at code as physical infrastructure. And, I want to leave you with a forward-looking thought that builds on everything we've explored today.
Oh, okay. Let's hear it.
Right now, human engineers are sitting in meeting rooms using frameworks like MCDA to manually balance latency, cost, and carbon. But we are rapidly approaching an era where AI agents will be empowered to autonomously rewrite, scale, and redeploy their own system architectures on the fly to meet real-time demand.
That's a little terrifying.
Right. When software starts architecting itself, what parameters will those AI systems optimize for? Will they prioritize millisecond speed, corporate cloud costs, or will they actually understand the thermodynamic limits of the grid?
Wow.
And more importantly, as they continuously restructure our digital foundations in the background, will human engineers even be able to comprehend the invisible environmental trade-offs they're making on our behalf?
If a physical building is sinking, you can see the cracks in the foundation. But if an AI builds a digital foundation that slowly drains the power grid, in the pursuit of microscopic latency gains,
Yeah,
we might never even see it happening.
exactly.
That is a massive paradigm shift to think about. Thank you so much for joining us on this deep dive. Keep questioning what's under the surface.